Okay. So this is the second video of the transformer architecture videos. And this video is dedicated to the attention mechanism. Okay, so we'll start with the terminology and move on to understand what is the attention mechanism. If we go back, so this is from the first video. So we already talked about how the tokenization works, basically taking a sample and breaking up the sample into small pieces. And the next part is the position information, adding the position information. We'll skip that for now and come back to it later. Essentially, what you have to keep in mind is the position information is just an alteration either by addition or some other operation that its purpose is to kind of like preserve the information about the specific position of each token. Okay, but we'll stick to the details for now. So basically, after these three blocks, we have a vectorized or vector representation for each of the tokens, for each of the parts of the sample. And kind of like the heart of the attention mechanism is the next block, which is the attention blocks. Kind of how do we merge or how do the different parts of a single object interact with one another and thus produce a more meaningful representation of the sample. Okay, and this is the attention mechanism. So first, let's talk about terminology. So the terminology of the attention of transformer comes from the world of information retrieval. Basically, we have a database, okay, with n elements inside the database. So basically, you have a table, and each element in the database has a key, is represented by some sort of key. So this is one column, and the next column is its value, the value of the element. And when I approach this database, I come with a certain query, okay? And you can think about both the query, the key, and value as vector representations. And I approach the database, and the output is the value VI, whose key has the largest inner product with the query. Okay, and this is what you see in the bottom. This is the output. So we have, again, each element has a key and a value, and I come with the query, and the output is some value whose key interacts strongly with the query. Okay, so this is kind of like the basic terminology of attention. And now we go back to where we started. So we have, by this point, a set of inputs. So these are the vector embeddings of the different tokens, okay, in some dimension, which is denoted by D. And what we do now is we compute for each token a key, a query, and a value, okay? And this is done by three matrices, usually square matrices. And these are trainable. Okay, so this is like part of the parameters that that are trainable, and we compute with these three matrices, W denoted WK, WQ, and WV, the key for each token, the query for each token, and the value for each token. Okay, so that's step one. Next, and the way I see it is that you compute a graph, okay? And the graph, so basically when we have a graph, and this is a directed graph, okay? So in a directed graph, you have nodes or vertices. These are the blue circles. And you have edges, and in this case, directed edges. Okay, so you have an edge from node I or vertex I to vertex J, and this edge has some weight, okay, and a direction. Okay, so here in our case, every vertex corresponds to a single token, and the weight is a function of the inner product between the query and the key. So this is very similar to what we discussed, right? In the information retrieval, the output or the element that whose value we output is the one that maximizes the query and the key. So this is kind of like the criterion we use. And the same goes here. Okay, so the edge weight is a function of the inner product, the edge weight between vertex I and vertex J is the function of the inner product between the query of vertex I and the key of vertex J. Okay. Essentially, the function is a softmax. Okay. Meaning that if I look at a single vertex I, and I consider all the weights, all the edges coming from other nodes to the vertex I, to the ith vertex, then the weights are computed by a softmax function. So the softmax is over the inner product between the query of I and the keys of the different nodes divided by square root of D. Okay. And so that ensures also that the weights are non-negative, right? Because the softmax it produces non-negative function. Also, the sum over all weights of the edges coming into a certain vertex I sum up to one. So basically, you can think about it as some sort of probability vector, right? As elements non-zero and sum up to one. But the way you use these is that once you compute the weights, then you update. So until now, only the key and the query played a part. But now, once you compute the weights of the edges, then you compute a new value for each node. And the new value is just a weighted average of all the values of the different nodes. And the coefficients are equal to the edge weights, which here denoted by A, okay, A to I. So this is the equation on the right. You update the value by a weighted average. Okay, so this is kind of how we compute the interaction between pairs of tokens in the system, right? So basically, we had a sample, we broke up the sample, we want to measure how different areas in the image, different words kind of interact with one another. This is the way we compute or measure the interaction by the softmax function. And then once we measure the interaction, we use that to update the value. Okay, and once the update is valid, we use the value to recompute an embedding. Okay, so the input to the attention mechanism is a set of embeddings, and the output in RD, and the output is also a set of embeddings, most of the time same dimension, but the new embeddings are already taking into account all pairwise interactions. So they contain much more information about the sample than the original embeddings, which are kind of a function of, so each in the original embedding, the embedding represents a single word. Here already, the new embedding represents not only a single word, but also a word and how it interacts with the other words of the sentence. So this is much more informative. Okay, so this is kind of the first part, the one we learned with additional elements. Okay, so we have the input EI to EN. This is the original embeddings, as we stated, of the different tokens. And then we have a layer normalization part. So layer normalization basically takes every input EI and divides it or removes the mean and divides by standard deviation up to some epsilon. So that I'm not going to go into the details of their normalization, pretty standard. But this is kind of like a small update done to the input embedding, also to ensure that they don't explode to kind of huge values. And then once these are normalized, they're given as input to the self-attention mechanism. So this is called self-attention, where every value is updated by its interaction with the other values. And you can see also the equation softmax of Q K transpose divided by square root of D times V. Okay, and once we have that, we add the original embedding, okay, with the output of the self-attention. Okay, so we don't throw out the original embeddings. We add them to the new embedding to get kind of like a new representation, which is the result both of the self-attention mechanism and the original embeddings. Okay, so this is kind of what happens here. Once we do that, then we reapply layer normalization, and we have another component, which is a fully connected feed-forward neural network, usually not a very deep one, 2, 3 layers. And this kind of gives, again, a non-linearity. So if, again, the self-attention mechanism essentially is a weighted average of the values, but once you go through the networks, then you added kind of like a non-linearity to the update process, which is also important. And again, you have kind of like this residual connection where you take the original input and add it back to the output of the neural network. Okay. So again, you can think about it as we have original embeddings to the tokens. We compute an updated embeddings that take into account all pairwise interactions and then apply some nonlinearity. So I say nonlinearity in the kind of like most general sense by applying a feed-forward network, and then you have an output. Okay, so this is a single, kind of referred to as a single attention block. Okay, and we'll see how the different components, okay, of the transformer architecture are built mainly from these kind of blocks.